representation of functions using power series. So basically, what you can do, which is kind of cool, is you take a function and you represent that function as a series. So you can actually create a series representation, which is really neat when you're trying to code things. So like if you have a really weird function and you need it to be more of a discrete representation, you can use power series. So representation of functions by power series. So an easy example is to look at a geometric power series. So f of x is equal to 1 over 1 minus x, which implies that it's equal to a over 1 minus r, right? Using our, just changing the notation really by letting a be 1 and x be r. We know that that's the same as a series, geometric series, where you find the total sum, right? We've dealt with this kind of series before, and we know that it's equal to this, which is basically that function. Where a is 1, r is x, right? So that would give us a series of x to the n. And see how it's the same. And of course, this would converge when the absolute value of r is less than 1. That is to say that absolute value of x is less than 1, which implies that r is equal to 1. Right, so we've done this type of stuff before. The only difference is now we have a radius of 1 and a interval of convergence, which is -1 to 1, right? Because it would be centered at 0. But anyway, so just rehashing what we talked about last time and the idea of geometric series and how they can be rewritten as a series. So this is a simple example of how a function can be written as a series, a power series. Okay. And of course, this is the rules for convergence here. So let's do an example. And they're going to give us where it's centered. And we got to create the series that. And once we find the series, we then have to figure out where it converges. So find a power series for the function centered at c equal to -3 and determine interval of convergence. Okay. So here's the function they gave us. And they're saying that it's centered at -3. So what you'd have to do is rewrite that x part. So you would take the function, and for the x, you would have to put x minus the -3 plus 2, right? Which is basically going to be 4 over x plus 3 plus 2, right? Um, yeah, leave it that way. I think that makes more sense. Now, if I want to rewrite it to look like a geometric, I should probably rearrange it this way. 4 over 2 plus x plus 3. Okay. So what I want to do is make this a 1, right? Because it needs to be 1 there. And then apply my geometric. So what I'm trying to do is force the function to look like this in order to change it to a power series. Okay. That's the goal. So I divide every single term by 2, which would give me 4 over 2, 2 over 2, plus x plus 3 over 2, which would give me what? 2 over 1 plus this weirdness. So I'm almost there. I just need it to be a minus, right? So that would be 2 over 1 minus a negative x plus 3 over 2. So now I have the exact form, which means that I can let this be my r, right? Which goes here. The a will be 2, so the series would be from n equals 0 to infinity of 2 times the r, which is this weirdness, to the n. Do you guys see where this came from? How I converted this guy to this. All right, so once you have this, determine what is the interval of convergence. So you apply all the stuff from 9.8, the power series chapter, and find out the interval and radius. So I see an n here, so I'm thinking the nth root test would be the way to go, right? So the limit as n goes to infinity of 2, that's the value, of negative x plus 3 over 2 to the n to the 1 over n, right? That's the root test. So that will be the limit of 2 to the 1 over n times absolute value will cancel, so I'll be left with a the root there, right? Sorry, the root will cancel, not the absolute value. Negative x plus 3 over 2. As n goes to infinity, so this will go to 0, which means this will go to 1, right? 2 to 0 is 1. And that will give us absolute value of negative x plus 3 over 2. That must be less than 1. Remove the absolute values will give us an interval. Like we did last time. So solve for x, which I'm out of space here. and we'll find the interval, which will then give us the radius. Okay. So I'm going to start with this piece on the next page. Do you guys have any questions so far as to what we did here and how we got the interval? All this right here is root test. That's giving us the okay. So let's continue on the next page. So I have -1 less than negative x plus 3 over 2. I don't have the absolute value anymore. Multiply everything by 2 gives you -2 less than negative x plus 3 less than 2. Dividing by negative will flip my inequality. Subtract by 3 will give me -1 x -5. Although this is the same as saying I'm going from -5 to -1. It's going to rearrange that so it's not weird, right? So this is my interval, but I need to check the endpoints, right? Let me see. With -1, we'd get yeah, it would diverge at the endpoint, so there's no point in doing that. So interval of convergence would be -5 to 1. So this power series that we created based off the function converges from here to here. So what is that? What is the center point here, right? The center we said was -3. So -3 in either direction, right? Here's -3. Here's -1. Here's -5. Radius of convergence would be 2, right? It's distance of 2. Are there any questions on how we created that? Right, let's do an easier one. I feel like we started with a hard one. Here we go. So here's the idea one more time. Find a power series for the function centered at c. So here's the function. And they gave us a c of 0. So that'll make it a little easier. I should also mention that I need to determine interval and radius of convergence. Okay. So it's already in that form, right? 1 minus r, where a is 4. So we can say here a is 4, r is 7x, right? So we know that this function equal to 4 over 1 minus 7x is equal to the power series of 4 times 7x to the n, where n goes from 0 to infinity, using the geometric formula. Because this is my minus r. R goes here. A is just in front, doesn't matter. This needs to be a 1, which it was. Great. Centered at 0 means I don't have to do that weird x minus 3 that I did last time. Okay. So we know by the root test that once we do the root test, we're going to end up with this piece here that needs to be less than 1. Right, just to save some time here. You would take this part, right, do the root test, and you end up with this. Let's remove the absolute value, divide by 7. Okay. So this is my interval. So interval I of convergence would be negative 1, 7 to 1, 7. And the radius would be the distance between here. So that'll be 1, 7. Because the center would be 0. Is there any questions on number 2? Okay. So now let's move on. So those examples were using only the geometric series formula. So now let's do Taylor series expansion, where we can take any function, doesn't matter what it looks like, and find the appropriate power series. Because notice the ones that we were doing, right, had to look kind of similar to a geometric sum. But like, what if it was an ln, right, or a sine or a cosine? You wouldn't be able to do this. So there has to be a general approach, and that approach is called the Taylor series. All right, so let's move on to 9.10 because that's more important. That'll be the last section of chapter 9. And I suppose you could start reviewing for exam. Taylor and Maclaurin series. Okay. Let me give you the theorem. So theorem form, the form of a convergent power series. All right. So the form for a convergent power series, if F is represented by a power series, f of x will equal the sum of a sub n times x minus c to the n for all x in I, open interval I, containing C. Then a sub n is equal to f to the nth derivative of c over n factorial, and f of x will equal f of c. Actually, if I put that down here, f of x will equal f of c plus f prime at c times x minus c to the first over 1 factorial over 0 fact. This is the 0th term, no derivatives. First term, first derivative, first power, 1 factorial. Second derivative, x minus c squared, second, 2 factorial. All the way until the general form of fn of c. I'll just put it down here. Not enough space. Fn at c times x minus c to the n over n factorial. So this is the general, well, let me phrase this better. Ouch. Yeah. So this is my f of x. So given any function, you can expand it into some series, a power series with derivatives, which is pretty cool. Okay. Let me give you the definition of Taylor and Maclaurin. If a function, f has derivatives of all orders, meaning you can take as many as you want at the center point C, then the series f to the n at C times x minus c to the n over n factorial is called a power series, a Taylor series, sorry. for, sorry, that's my train of thought, for f at c. If c equals 0, then you have a Maclaurin series. So basically it's the same thing, it's just Maclaurin is specific. You have, sorry. Give me 1 sec. Okay. Let's do an example. So let me teach you the procedure for creating the Taylor expansion. Because it's a little weird. So let's go step by step. Like how do we use this, right? And what does this mean? Find the Taylor series. So the questions would be asking you to find the Taylor expansion series centered at C for the function f of x equal to e to the negative 2x, where c is equal to 0. So since c is 0, this is technically a Maclaurin series, but Taylor is just more general. Okay. So what you do is you take the function and you take a bunch of derivatives until you should start to see a pattern. So there's a 0 derivative, right? Because I haven't done one. First derivative be negative 2e negative 2x, right? Second derivative would be 4e negative 2x. Triple derivative be negative 8e negative 2x. Anyway, the next thing you do is plugged in the c, right? So f of c would be f of 0, right? F of 0 would be 1. F prime at 0 is equal to negative 2. F double prime of 0 is equal to 4. F triple prime of 0 is equal to negative 8, right? So it's all given to me by plugging in the value. So you plug, I didn't show the work, but you see I'm just plugging in 0 here, right? E to the 0 is 1, e to the 0 is 1, e to the 0 is 1. So all these are just 1s. 1 times negative 2, 1 times 4, 1 times negative 8. So at this point, you need to start trying to, what's the word? Find a pattern. But let's go ahead and plug it in. Let's use the formula, right? This Taylor series expansion. So n equals 0 to infinity. F to the n at c times x minus c to the n over n factorial. So that's the formula, right? So we know that the first one first number, right, is going to be, this is like f0 at c, right? So this would be 1. Let me make more space here. So the first term, the 0th term, is 0 factorial times 1 minus x minus 0 to the 0. That's the 0th term. Plus negative 2, right? That's this number, times 1 factorial times x minus 0 to the first, plus 4 x minus 0 squared is the second term, or the 2 term, whatever you want to call it. Negative 8 for the third, right? And then that keeps going forever. So, this is the Taylor expansion formula. So what you got to do, right? Remember, the 1, negative 2, 4, 8 came from here. X minus 0 comes from the formula. The factorial is from the formula. So let's try to figure out what the, what's the word? The pattern is going to be. So let's simplify this. X minus 0 to the 0 is going to be gone. That leaves me with a 1, right? First term is a 1. 1 factorial is 1. X minus 0 to the first is 1. So this becomes negative 2x. This becomes 4x squared over 2 factorial, 1 factorial. I'm going to go ahead and write it down here. 1 factorial. This becomes negative 8x cubed over 3 factorial, and it keeps going. So that's going to be, so looking at this, you need to find the pattern and create the power series. So what the hell is it going to be, right? It's going to be tough here because we got to think. So it's positive, minus, positive, minus. So if there's for sure an alternating part, so let's start with that piece. So at 0, it's positive. At 1, it's negative. At 2, it's positive. So yeah, this one works. So it doesn't have to be n plus 1. It would be just negative 1 to the n. Okay. Now let's incorporate the numbers. So we have 1, 2, 4, 8. So that's powers of 2, and there's an x. So that's created with 2x to the n. Because when n is 0, I get 1. When n is 1, we get 2x. When n is 2, I get 4x squared. You see that? See how this works? So this covers the top part. This covers the alternating part. Now I need the part for the factorial. Simply put n factorial. So this is the answer for the Taylor series centered at 0 for this specific function, e to the negative 2x. So the procedure is you take a bunch of derivatives, you plug in the c, and you try to find that pattern. But before you do that, you plug it into the formula, right? This is going into the formula. And then you do x minus whatever c they gave you, and you count from 0 to whatever. You simplify it and you try to find a pattern that will create this for you. So that's how you find the a sub n for your power series or your Taylor series. And you can do this with any function that has uh, n derivatives, I guess, like derivatives of all orders. It's pretty neat how you can change a continuous function into a discrete series representation. It's really handy for programming because there is no infinity inside computers, right? Are there any questions on number one? These take a while, so you probably only have like one of these on the exam because there's a lot of steps. All right, let's go to the next problem then. Another Taylor series. This time, let's try with a sine function. When you can see the Taylor's expansions for sine and cosine are kind of weird, but it can be done because sine and cosine have infinite derivatives, right? You keep going forever. Find the Taylor series centered at C. For the function f of x equals to sine x, where c is pi over 2. All right, so let's take a bunch of derivatives, like maybe 4 or 5 of them, plug in c, and see what the pattern is, right? Now, this one I'll show a little more steps. So zero derivative is just this function. First derivative will be cosine, right? Second derivative would be negative sine. Notice how I'm back to sine, but it's negative. Triple derivative, the negative cosine. Fourth derivative is equal to sine. So it took 4 derivatives to get all the way back to what I started with. So everything after that is just going to repeat, right? So who cares? So now plug in the pi over 2 into the zero derivative. That gives me sine of pi over 2, right? Which is 1. First derivative of pi over 2 would be cosine of pi over 2, which equals 0. Negative sine of pi over 2 gives me a negative 1, right? Okay. Third derivative of negative cosine of pi over 2 is equal to 0. And then the fourth, well, we're back at, it's supposed to be a 2. Back to sine, right? So that's going to be 1. And if we kept going, we would see that it just keeps repeating itself, right? So if I did 5, 6, 7, right, derivatives, I would end up, sorry, I can't even read that. Maybe I could make that look better. You will see that this will keep going, right? If I keep doing the derivatives all the way down, I'm going to get uh, 0. No, actually. Yeah. And then the next one would be -1, and the next one would be 0, and it'd be 1 again. So you see how it repeats 1, 0, -1, 0, 1. So it's these, then these again, and then it keeps going, right? Forever, I guess. So let's expand the Taylor series formula at c equal to pi over 2, plug in our values, and see if we can create the series itself, the powers. Okay. Here's the formula. All right. So that would equal, well, first one is 1, right? So 1 times x minus pi over 2, because that's my c, to the 0 over 0 factorial. Then plus 0 times x minus pi over 2 to the first over 1 factorial, plus -1 times x minus pi over 2 to the second over 2 factorial, plus 0 again, x minus pi over 2 to the third over 3 factorial, plus 1, back to 1, x minus pi over 2 cubed, 4, sorry, over 4 factorial. Okay, then it starts over, so 0 times x minus pi over 2 to the fifth over 5 factorial, plus, after 0, it's, so 1, 0, -1 times x minus pi over 2 to the 6 over 6 factorial. Anyway, it goes on forever, right? Who cares? But notice how there's pluses and minuses, but also there's a bunch of zeros. Like these 0 terms are going to disappear, aren't they? So we got to, when we create our formula, we got to figure out a way to not incorporate those terms. These happen at every odd term. Notice that 1, 3, 5, 7. Also, the ones that do stick around go from plus, minus, plus, minus. So I need to create a formula that alternates only on the ones that stay. Or I'm sorry. You need to create a formula that zeroes out those odd terms or doesn't create them at all and alternates appropriately. All right, so find the pattern. So that's the hard part, finding the pattern. So once we expand it and plug in everything into the formula, that's what we got to do. So notice that this happens only the even ones stayed. So what I'm going to do is put 2n, right? So at 0, it's 0. At 1, I get 2. So that stays. Notice that. And on the bottom, I only wanted to keep 0, 2, 4, 6. So meaning on the bottom, I need to have only even numbers, so 2n. So no matter what n I choose, it will be even. Next thing, so this deals with the skip. This makes sure I only get the evens, factorials. Now I need to deal with the alternating part. So the first one must be 0. So it'll be even, or be positive. So this will alternate every other term, or every term. This will help me skip the ones I don't need, and this gives me only the ones I want. So this will work, right? This will create, just in case you can't see it, this creates negative. Sorry. Zero x minus pi over 2 to the 0 over the 0 factorial. Notice how this is the first term, right? Does that take care of this third term? That'd be negative 1 to the 1 times x minus pi over 2 to the 2 times 1, which gives me the 2. See that? So this works. And n would be 1, so it'd be 2 times 1 factorial, which gives me this. So you got to be clever and try to figure out what is the formula that makes this happen. Okay. Let me make a little note here. Evens only is 2n. Odds only is 2n plus 1. Okay, so this kind of helps you. And if you wanted to go plus, minus, you need to use negative 1 to the n if we start at 0. If you want to start at minus, plus, then you want it to start at negative 1, do n plus 1 to just adjust it. See what I mean? If you wanted to do plus, minus, plus, minus, plus, then you would need negative 1 to the n plus 1 divided by 2. If you wanted plus, minus, plus, minus, plus, you need negative 1 to the n times n minus 1 over 2. So these are kind of helpful if you have difficulties in imagining what will do this for you. Here's some shortcuts, shorthand, I guess. Anyway, let's take a short break because my hand hurts. It's 9:06. Let's come back about 9:15. And we'll start doing review or some homework questions. Hope you guys are still awake. Do you guys have any homework questions you want to work on or you've been stuck on? I know this chapter can be challenging. If you want to work on a few you're struggling with, let me know. If not, I'm going to start on the final review, or the review for exam 9. Exam on chapter 9. Okay, I opened chapter 9 notes and the review as well. One second. Okay, here's a review. Okay, so here's a review. It'll start off with some sequences. It starts off pretty easy. It says list the four elements of the sequence. Literally, you plug in 1, 2, 3, 4, and then you get 4 terms, right? So this guy, you find the limit of the sequence to determine a divergence or convergence, right? So the first 1, 2, 3, 4, 5 questions are all about sequences. And then 6, 7, 8, 9, 10, 11, 12, 13 are all about series. 14, 15, 16, 18. Yeah, so the rest are all series except when it gets to here, where it says radius of convergence, that's when the power series starts. So power series, power series, power series, power series. And then here we get to Taylor and Maclaurin, the last 3 questions, which is what we did today. Right. So let's just go through these and see how far we can get. So this doesn't look too bad. Just, oops, there's some water here. All right. So exam 4 over chapter 9. Review, I guess. Number 1 is pretty basic. Write the first for terms of the sequence. N plus 1 over 3n minus 1. So a sub n, obviously, is this sequence that they gave us. So all they want is, what is a1? Well, plug in 1, that'll be 1 plus 1 over 3 times 1 minus 1. So that'll be 2 over 3 minus 1, which is 2 over 2, which is 1. Right? 2, 3, 2 minus, yeah, that's right. Okay, so now do a2. So that'll be 2 plus 1 over 3 times 2 minus 1, which would be 3 over 6 minus 1 over 3 over 5. A3. So you just do that the whole way. Let's move on to number 2. Save time here. It's not difficult. Number 2 says find the limit of the sequence. And indicate if it converges or diverges. Right, so the limit as n goes to infinity of 2 plus 5n over 4 plus 9n will equal to 5 over 9, which means, so since the limit of an is finite, then the sequence converges. So for sequences, as long as you have a limit, and that's it. Okay. So 3, let me go ahead and show you. All right, so here's the other 2 terms for number 1. Here's the limit. If there's a limit, then it converges. So on your exam, you'll say you'll explain that, right? Since the limit is finite and converges. If it was infinite or the limit did not exist, you would say diverges. So 3, 4, 5 are all the same thing. Just find the limit of the sequence. So let's move on to series. So this guy is a actually it's a, just find the sum of the series. So since it's a geometric, you can apply the geometric sum formula, and you'll be done. As long as r is less than 1. I don't know what number that is. 1, 2, 3, 4, 5, 6. And the sum of the series of 9 over 7 to the n. So remember that the sum of a geometric, right? The formula says the sum of a over 1 minus r. I'm sorry. Shoot, let me find it. Double check my formula here. Okay. Yeah, so 91, I think. We did the geometric. No, 92. Let me find it. Yeah, here we go. So the formula was all right. So sorry, lost my train of thought there. I don't know what the heck I was writing there. A to the r is the formula, which is equal to a over 1 minus r. So our a is equal to 9. Or no, I'm sorry. Actually, yeah, that's right. R would be equal to 1/7 because I can pull that 9 out. Okay. So pull out the 9, the sum. So we got 1 over 7 to the n, which would give me 9 times 1 minus r, which is 1/7, which is 9 over 7 over 7 minus 1 6/7. So it'll be 9 over 1 times 7 over 6, which is what? 63 over 6. Three goes into both, right? Let me see here. That sum should be sorry, getting tired. 21 over over 2. So there's my sum. So since r is less than 1 and then the series converges and the sum is 21 halves. Any questions on number 6? Okay. Number 7 is another geometric. Determine the geometric series converges or diverges. If it converges, find its sum. That's what we did earlier. So 1 plus -9 plus -9 squared plus -9 cubed, right, forever. So what I recommend, find the formula for this. So this is basically the geometric series starting at 0 to infinity of -9 to the n, right? At 0, you get a 1. At 1, you get -9. At 2, you get -9 squared. At 3, you get -9 cubed. So yeah, this works. But right away, you can see, since r is equal to -9, I should say, absolute value of this is greater than 1, then v the geometric series diverges. Okay. So number 8, 9, sorry, number 8 is another geometric. So let's move on to something else. Move on to number 9. Okay. No, you know what? We'll stop here. It's kind of a lot of stuff already. So on Tuesday we'll finish the review. Please bring questions if you have them. I'll open the exam up today. You can take it anytime between today and next Thursday. But next Tuesday I'll finish the review and we'll figure out chapter 10. All right. So we'll stop here.